Welcome back to Emerging Patterns, the annual conference on complexity organized by Paleolithic. I'm Kevin Xiao from the School of Electrical and Electronic Engineering at TU. I'm honored and pleased to introduce to you our first speaker today, Prof. David Christian. David Christian is the director of the Big History Institute at Macquarie University, Sydney, and he is also a co-founder of the Big History Project with Bill Gates. You know, human being is probably the only creature on this planet who intentionally keeps record of their history. Not only we record our history, also study on it, we even teach the next generation about it in the hopes that we can learn something from it. I still remember when I was a secondary school student, we learned the history in this way, that we studied the natural history and human history. Then for the human history part, we studied the Chinese history and the world history. Then for the Chinese history part, we studied one dynasty after another. That was the way how we interpret the world. Big history interprets the world, if I'm not wrong, in a totally different way. It goes all the way back to 13.8 billion years ago when this universe started, and look at something that is very, very big. The first time I watched David's TED Talk about big history, I was totally amazed. For me, that was, eye-opening experience. I got to believe that such an approach will actually open new possibility for us to, understand our past. And also, it will affect, to the way how we will actually handle our future. Well, without any further delay, ladies and gentlemen, please join me to welcome our speaker, Prof. David Christian. David.
Thank you, Kevin. I'd like to thank Jan and his colleagues for inviting me to this wonderful conference. I had a fabulous day yesterday, and I learned a lot. And as a result, I'm tempted to rethink some of the things I'm about to say, but I'll probably stay with what I have already. I love this image. It's already iconic. It's familiar. It's time-lapse photography from the International Space Station. I put it up because it captures in a sort of instinctive way, the feeling of why I love big history. It helps you see our planet, our home planet in space, which those early pictures from the moon did. So it gives you a glimpse of our planet as one tiny mote of dust in a huge universe. But it does something else. It reminds you, this machinery here, of the astonishing fact that we humans have figured out when the universe began. We have learned to see the universe as a whole, and that is staggering. So it's a great way of putting human history in the history of the universe. Now, this talk reflects 25 years of teaching big history, that is to say, teaching courses on the history of the universe. I coined the phrase big history. I'm not completely happy with it, but we seem to be stuck with it. Anthropologists tell me it's phallic, but we're going to have to live with it. So these are the ideas that have really come out of teaching big history, writing about big history, and as you'll see, I'm convinced this is powerful educationally, but also I have the hunch that it's a powerful way of providing that it generates research agendas that cross multiple disciplines. So what is big history? This is a definition from the website of the International Big History Association, which was founded just 5 years ago, and of which I was the first president. The attempt to understand in a unified, interdisciplinary way the history of cosmos, Earth, life, and humanity. And that's a pretty precise definition, but it won't really give you a feeling for what big history does. And that's what I'm going to sort of try to do in this talk. A short history of big history first. At first, I thought I was being astonishingly original in trying to teach a history of the whole damn thing. Really, that's how I started out. I thought, wouldn't it be fun? I have no idea how to do it, but wouldn't it be fun to teach the whole damn thing? Then eventually I realized anthropologist friends pointed out that I was not being original at all, that most human societies have done this same thing. We call them origin stories, and we think of them sometimes rather patronizingly because we see them from outside. But origin stories in pre-literate societies, in literate societies, are rich collections of stories based on the best available knowledge, and often on a lot of knowledge. And what they do is they help people place themselves in space and time. They're immensely important educational and thinking tools. They provide the largest possible framework for the past. And I realized eventually that that's really, I'm doing the same thing. I'm trying to do the same thing, but using all the information of modern science. And the remarkable thing I've slowly realized is that we don't teach such a story in our secular educational institutions. And for all sorts of reasons, I think that's a big mistake. It became possible to tease out an origin story based on science only in the second half of the 20th century. H.G. Wells tried to do this after World War I. He said the science wasn't detailed enough. Above all, he didn't have any absolute dates before the first Olympiad, which I think was 776 BC. New dating techniques, beginning with C14 dating, mean that we now can come up with a pretty trustworthy skeleton of dates that goes back to 13.8 billion years ago. And the sciences themselves have become more historical. Above all, cosmology, which in H.G. Wells' time was not a historical science. Cosmologists still lived within a Newtonian universe that was infinite in time and space. It had no history. So it made sense to think that history is something characteristic of humans, maybe of living organisms, but it's confined to those groups. Now we know that history is characteristic of the entire universe, of cosmology itself, of the history of the planet, of the history of life on Earth. And since then, many scientists and educators have begun in different ways to tease out this story. I think Carl Sagan was doing something like this in Cosmos. Asimov, I loved reading as a youngster. John Gribbin inspired me. And Eric Chaisson, an astronomer who's taught big history courses in Boston for many years and whose work has inspired many of my ideas. I began teaching big history without knowing any of this in 1989. I just thought it'd be fun. It was a mess, our first course. We didn't know what we were doing. But I think slowly over 25 years, a story has come into focus. And I think it's a pretty good story. Most of its details are based on pretty robust science. In 2008, Bill Gates stumbled on a series of lectures I did for an American company, the Teaching Company, on big history, 48 half-hour lectures. And he actually sat through the whole thing, on his exercise bike. And he decided this needed to be in schools, which was something I'd always thought, but I had no idea where to begin. I thought of rocking up to the Department of Education in New South Wales on Macquarie Street and saying, here, I've got this great course, why don't you bung it into the schools? Of course, I'd been laughed at. But what Bill Gates has done has enabled the building of a free, online, high school syllabus built in collaboration with teachers and students that is now available for free for any schools in the world. And it's now being taught in hundreds of schools, mostly in the US and Australia, but some in Korea, some in the Netherlands. We're hoping we'll be teaching it in Hong Kong soon. I'd love to be teaching it in Singapore. In 2012, Macquarie University created a Big History Institute to support both this educational project and to hold conferences that pursue research agendas across multiple disciplines, and some of them I'll be touching on in this story, and I hope I can persuade you that this account I give of the history of the universe is oozing with questions that take you across disciplines. So why do students and educators need it? It crosses borders, it builds connections, it does interdisciplinarity in a natural and coherent way within a narrative. This is a report from the British School Inspection Agency, Ofsted, in 2007. The majority of adolescents leave school with bits and pieces of knowledge that add up to very little and fail to inform or even to connect with present realities. I see big history as part of the solution to that very serious problem. It's not a British problem. I think it's a problem of secular education throughout the world. And this is why Bill Gates supports the project. He said, I wish everyone could take this course in an interview. Big history shows how everything is connected to everything else. It made me wish that I could have taken big history when I was young. We found it gives students, it empowers them because it gives them a sense that there is a perspective from which you can sort of see the whole of knowledge. And that is deeply empowering. This is a student in one of our pilot schools in Brisbane. Emily wrote, "Big History has explained how seemingly isolated events we are taught at school fit in the context of the universe, its history, and how this may have further implications in the future." Emily and her generation will be running the shop in 25 years. So a foundational story that can give them a good perspective from which to think about where our world is going is very important. So this is why I love using this image from Van Gogh, because it captures this sense of interdisciplinarity. We have here stars on the cosmos, so we've got astronomy and cosmology. We've got planet Earth, so we've got geology and the earth sciences. We've got water, where life evolves, so we've got biology and we've got chemistry. We've got cities, churches, and human civilization, so we've now crossed into the humanities. We've got anthropology and history. We've got electric lights, so we've got modernity, we've got science, we've got technology, and this is the most important thing of all. There's you and me at the center trying to figure out how we fit into this vast, ramshackle story. So that's why I love using that as an icon. I believe that big history is a powerful way of solving the problem that C.P. Snow talked about in his famous lecture on the two cultures. He was both a scientist and a novelist. He did cross the cultures. And he described science and the humanities as distinct cultures in an anthropologist sense. They didn't know how to talk to each other. And he thought this was tragic, like the Cold War. It deprived us of intellectual synergies that might have been generated through more active exchanges. It deprived us of knowledge, of insight, of understanding. And he wrote, "The clashing point of two subjects, two disciplines, two cultures, of two galaxies as far as that goes, ought to produce creative chances. The chances are there now, but they are there, as it were, in a vacuum, because those in the two cultures can't talk to each other." And that, I think, put very well why we really need interdisciplinary education and research. So much fundamental research has taken place very successfully within disciplines in the last 150 years that now more and more of the problems, the important problems, lie between disciplines. So in this talk, let me stress, I'm not a scientist. I'm a historian. I'm originally a historian of Russia. I've always been interested in science and its relationship to the humanities. This is an attempt to give you a feeling for the big history story, how it can usefully frame discussions of today's world. I think that's why I've been invited now 3 times to the World Economic Forum. It's partly reflected glory from Bill Gates, but it's also, I think, because they're persuaded that this does provide a framework that is helpful for thinking about contemporary issues, how it can link the sciences and humanities, how it can unify education. This is an expanded version of a talk that I gave at the World Economic Forum in January, just 6 weeks ago, which if you're interested, you can probably find by just Googling David Christian World Economic Forum 2015. And that, by the way, was introduced by Al Gore, who then gave a talk which was an update of An Inconvenient Truth. And the two actually worked together very well, which was lovely. Okay, the 2-minute course. Here's the 2-minute course, and it consists of a list of dates. Now, those of you who aren't familiar with this, don't worry if this seems like a blur. I'm going to come back to them. The universe appeared 13.8 billion years ago. Our Earth and solar system appeared 4.5 billion years ago, though we now know that planets and solar systems are normal parts of the cosmos. And the first ones could have appeared within 2 billion years of the Big Bang. Living organisms on this planet appeared probably by 3.8 billion years ago, though once again, increasingly, I think there's probably a majority of scientists interested in these problems would argue that it's quite likely that the universe is crawling with life, bacterial life, certainly. The first multicelled organisms appeared in large numbers 600 million years ago, in small numbers maybe a billion years before that. So there's clearly complicated stuff that takes you from bacteria to multicelled organisms. I often think if you were a bacteria and you looked at an organism like me, it would be looking like the Empire State Building or the Burj Khalifa in Dubai. These are colossal structures. How did they get there? The dinosaurs are wiped out 65 million years ago. Now, that date appears not just because dinosaurs are cute, my students love them. It is important for us. If an asteroid clearly played a crucial role here. Walter Alvarez, by the way, who discovered that, teaches big history at Berkeley within a geology department. If that asteroid had been on a trajectory 5 minutes earlier or 5 minutes later, it would not have hit the Earth, the dinosaurs would still rule, and I can guarantee you and I would not be here. So that's an important part of our story. It allowed this mammalian radiation of which we're a part. The first hominines appear about 7 million years ago. Our species, there's a range of dates. I think 200,000 years is a good date. Some would say 70,000 years. And you can quibble about this, but that's very recent. The first agricultural societies about 10,000 years ago. The first civilizations and documents about 5,000 years ago. I can't resist pointing out that this is the point at which my intellectual tribe, the historians, start waking up and showing some interest in the story. And I'm so tempted to say, actually, there's some interesting things that happened before that, but that's an argument that'll take time. Industrial Revolution, 250 years ago, human societies enter space 50 years ago. Now, if that's a blur of dates, let me run through a similar list in a slightly different format. I found that students can get a sense of the shape of this story much better if I divide all the dates by 1 billion. And there's a very good biological reason for this. Natural selection designed us to deal with time periods of a few years, maybe up to a century, but our brains don't need to cope with larger time periods, so we don't. If anyone says they can imagine 1 billion years, they're lying. This is wrong. We have to deal with it. We can't imagine it. So we can deal with 13 years. So let's imagine the universe appeared 13 years ago and recalibrate. The Earth would have existed for about 5 years. Large organisms with many cells would have been common from about 7 months ago on this time scale. The asteroid that wiped out the dinosaurs would have landed 3 weeks ago. Hominins, that's bipedal great apes, would have existed for just 3 days. Our own species, Homo sapiens, would have existed, I don't know how many of you are playing, but if you want to guess, before I throw up the date, and the answer is 50 minutes. You were probably already having coffee when humans appeared. Agricultural societies would have existed for 5 minutes, the entire recorded history of civilization for 3 minutes. Remember, this is on a scale of 13 years. Modern industrial societies for 6 seconds. As a historian, I think this is a fabulous way of placing human history in a larger context. Some historians get a bit worried at this point. I see no reason to get worried, but it's realism. So 1 second ago, we entered space, and this is where we live. So this is a story that operates at multiple scales in space and time. And each of those scales can show you new things, just as those famous pictures of the Earthrise from the moon helped us see the Earth in new ways. Each perspective can add new things. Add all these perspectives together, and you've got a very rich and powerful story. This is me telling this story in Tianjin in last August. Now, I'd like to give you a sort of conceptual toolkit for grasping this story. As we've worked on this, myself and others interested in this project have found that there are ideas that seem to be able to cross disciplines very easily, and they're immensely helpful. We're having to sort of develop almost a new vocabulary, a new set of concepts. And here are 4 of them. And they're very relevant to this conference, by the way. The first is complexity. Well, the language being used for this conference is emerging patterns, but I think we're talking about the same thing. The early universe was simple, then more complex things emerged. Stars, life, then us humans. And it's because we represent a very high level of complexity that this story is really relevant to us, even though we appeared so late. The second concept, emergence. Balázs talked superbly about emergence yesterday, so I don't need to spend a lot of time on it. New things appeared, utterly new. We struggle to explain where their qualities appeared from. So if you take 2 colorless gases, hydrogen and oxygen, you take 2 atoms of hydrogen, stick them together with an atom of oxygen, and you do that many times, suddenly you get wateriness. Now, where did that come from? That, for me, captures the sense of emergence, and it happens over and over again in this story, each time we see a new form of complexity. Then energy flows. What drives emergence? Well, I'll come back to this question at the end, because I don't think we yet have good answers. The second law of thermodynamics, the law of entropy, seems to be telling us that things, by and large, ought to be getting simpler. They can get more complex only if there are gradients that allow flows of free energy that can do work to construct more complex things. So wherever you have complex things, you should look for the energy flows, and I'll try to do that. And finally, the idea of Goldilocks conditions, a very simple idea. Complex things did not appear in the universe as a whole. The universe as a whole did not get more complex. They appeared in very specific pockets in the universe where the right Goldilocks conditions existed. Not too hot, not too cold, not too dense, not too empty, and so on. So these four concepts will take us quite a way, I think. And this is a graph from the work of Eric Chaisson, an astronomer who's taught courses like this in Boston for many years. And I've borrowed one of his key ideas, which is about energy flows. So let me take you through this graph. This scale here is a logarithmic scale showing energy rate densities. That is to say, the amount of energy flowing through a given amount of mass in a given amount of time, through a gram per second. And he then does some back-of-the-envelope calculations. He would not claim too much precision for them about a series of entities. So the sun, about 1 erg per gram per second. That's the order of magnitude, okay? Modern human society, about 1 million times that figure. Now, Chaisson's argument is that if you need energy to create complex things, maybe we have a very rough metric here for complexity. So maybe more complex things depend on denser energy flows, and they have to manage that flows. And that may explain the horizontal axis, which shows how long these entities live. So the sun, our sun will live actually for probably 9, 10 billion years. You and I, if we get lucky, 100 years. Now, maybe again, this is logical. You know, if we represent a higher level of complexity, we have to manage denser energy flows. That task is more difficult, and therefore we're less likely to survive as long. So if this is right, then there's a rough sense in which complexity probably correlates with fragility. Sustaining large energy flows is difficult. Now, with these ideas in mind, in our teaching, we adopt this simple skeleton of 8 thresholds of increasing complexity. Now, we could argue it's a convenience. It's not a sort of scientific theory. We focus on 8 thresholds of increasing complexity, and this seems to create a fairly compelling story that works well in educational environments. The first is the Big Bang itself, creating something where we don't know what existed before. The second is the creation of the first stars. The best date for that is about 560 million years after the Big Bang, and that's a very recent date, by the way. Then the creation of new chemical elements, a chemically richer universe that could create new materials. Then the creation of planets, and at this point we'll focus on our solar system. Then the creation of life. Finally, the creation of humans. Now, again, this is the point at which we cross from the sciences to the humanities. So it's a very interesting segue. And it raises the question whether this is not anthropocentric, to think that the appearance of humans should count as a threshold in this story. Well, I'm going to try and argue. I hope I can persuade you that this is a very significant threshold. Then 2 more within human history. And at this point, let's confess, we are being anthropocentric. But then when I teach, most of the people in front of me are human beings. So this is the story they're interested in. So that's my justification for going anthropocentric towards the end of the story. So here's where new chemical elements began to appear. Here's where our solar system appeared, where life appeared, and that's where we appeared on this timeline. Now, again, to see if any of you are playing, when were the dinosaurs wiped out? Could you mentally place that event on this timeline? Happened a long time ago, right? 65 million years ago. So you may be tempted, like many of my students, to be sort of moving way down here until you realize that no, the Earth, the solar system was created there. So it had to be back earlier than that. And in fact, it's about there. Okay, very recent event in this story. So here's the story. The early universe was simple, had very little structure. You can think of it, and I'm thinking about 500,000 years after the Big Bang. a thin mist of hydrogen and helium atoms, a tiny smattering of lithium and beryllium. Photons of light. This is all embedded in dark matter, which we don't fully understand, but we know it's there. And the whole thing seems to be at a very uniform temperature. This is from a recent book on complexity and the arrow of time by Charles Lineweaver and a number of other very distinguished scientists. And in their introduction, they say, whatever measure of complexity we use, because the idea of complexity itself is still unstable, there was little of it in the first tens of millions of years after the Big Bang. Now, how do we know? Well, we can actually measure the distribution of energy in the early universe by tracking the cosmic background radiation, which is what the Planck satellite did in this, again, already iconic image. And what you need to know is the difference between the blue and red areas is about 1/1000th of a degree. So this is a very homogeneous universe in terms of temperature. That's what I mean by saying it's simple. There are no galaxies, no stars, no heavy elements or planets, and no living organisms, certainly no human beings. Then, over 13.8 billion years, more complex things emerge. Now, most of the universe is still simple, but where the Goldilocks conditions are right, such as the surface of a rocky planet, our Earth, and where there are gradients that allow flows of free energy, more complex things have emerged with new qualities. It's an interesting story for us humans because we represent probably the highest level of complexity we know. Atsushi yesterday said the brain was the most complex thing we know. I think a structure that links 7 billion brains through the internet is arguably even more complex than the individual brain. So, threshold 2, how do you make stars? Well, gravity is the main actor here. Think of that thin mist. Now, there were tiny inhomogeneities in it, and that means that some areas were slightly denser. And if you remember Newton's laws of gravitation, you'll remember that where there's more mass, gravity is more powerful. So what gravity does is starts clumping this universe. And this is a series of computer simulations about what may have gone on over many billions of years. So it turns this thin mist of hydrogen and helium into a vast number of clouds, and those clouds are collapsing. As they get denser, gravity becomes more powerful. They collapse more and more over millions of years, and they start heating up at the center. And when the center crosses a temperature of about 10 million degrees, protons, which have now been stripped of their electrons, start fusing to form helium nuclei, pairs of protons. That's the same reaction as in a hydrogen bomb. There's a huge amount of energy released because some of the matter is turned into pure energy. And so at the center of each of these clouds, there's now a sort of furnace. And that furnace stops the cloud collapsing. So there's a balance between this energy being released at the center and gravity. And now you have a star. And that's how the first stars lit up, probably from about 560 million years ago. Now, a universe with stars is already much more interesting, I think. Stars themselves have structure. They gather together in these huge societies we call galaxies. Galaxies have very rich structure. And there are now lots of gradients of heat. We can think of stars as kind of hotspots dotted through a very cold, largely empty universe. There are gradients of heat, of density, of gravity, and so on. So much greater possibilities now for building new forms of complexity. Now, I said I'd track the energy. Where does the energy come from? Well, I've already said it. From fusion in the center of stars. That's the energy that maintains this particular form of complexity. Now, threshold 3. Our universe has hydrogen and helium in it. You can't do much with hydrogen and helium. Helium's completely inert. Hydrogen's interesting, but it needs something to work with. So where do the energy flows come from that create new elements? And the answer is inside dying large stars. So a very large star at the end of its life, when it's run out of protons at the center, the furnace at the center will stop. It'll shut down. Now gravity takes over. It collapses that star so violently that it generates higher temperatures than existed before at the center. Now you can take the helium nuclei that have filled up the center, they're clogging up the center, and you can combine them to form all these elements up to iron in the periodic table. That's why they're so common: carbon, neon, oxygen, silicon, iron. And they form in layers inside large clouds. But then eventually this process stops, and the cloud, and this star, if it's large enough, will collapse again so violently that it will explode in a supernova. And in just a few minutes, temperatures are so high that you can create all the elements of the periodic table. And that's how you get a chemically enriched universe. So these new elements are then scattered like confetti into the space between stars. And if you go to the NASA wonderful astronomy picture of the day site, which I love browsing on, you'll very often see beautiful pictures of these kind of dust clouds between stars. So what's happened to the universe? Well, these pie charts may give you a feeling for this increasing chemical complexity. Here's the early universe that I've talked about already. About 76% hydrogen, 24% helium. Now, what starts happening is inside stars, hydrogen burns to form helium. So if we look at the abundance of chemical elements today, this is what we have. Less hydrogen, about 70%, 28% helium, but that is where we find the chemical richness, that little wedge of materials at the top. May seem a sort of narrow basis for further complexity, but we'll see how this works. This, incidentally, is from a wonderful book by Lawrence Krauss, A Universe from Nothing, where he gives data about a trillion years in the future. And I thought you might find this interesting. 60% helium. This is a trillion years of stars turning hydrogen into helium, turning protons into helium. 20% hydrogen, 20% the rest. Now, with new materials, new types of materials, with new emergent properties, you can make new things. You've got motes of dust, you've got silica, you've got water, you've got grains of snow. You can make rocky planets. And rocky planets are peculiarly interesting, much more interesting than the gassy planets. And here's why. This is the abundance of chemical elements in the Earth's crust. Now, I don't know how quickly it'll be obvious to you that this is very different from the pie charts I've put up so far. The first thing is there's no hydrogen or helium. The amounts are so small that they don't show up here. Instead, 46% oxygen, 27% silicon, 8% aluminium, iron, and so on. So this is chemically a very chemically enriched environment. And the reason seems to be because the solar wind, energetic particles from the sun, drove away most of the lighter elements early in the history of the solar system. So they drove away most of the hydrogen and helium. It gathered at the orbits of Jupiter and Saturn and Neptune and clustered around them. They may have Earth-like cores, but all that hydrogen and helium gathered outside those cores. So that makes the Earth, the rocky planets, very interesting indeed. I love this slide because it was made by a former student of mine, Martin Schuler. And I think it's probably not a bad representation of the Earth about 3.8 billion years ago, which is when we think the first life probably appeared. You've got water in liquid form. That's fabulous for chemistry because in gases, atoms are just traveling too fast to link up. In solids, they're locked. In liquids, they can cruise past each other and hitch up. So it's a great environment for chemistry. You've got heat and energy both from inside the Earth, its hot core, and also from the sun. So you've got the energy flows, and you've got this rich chemical mix. Now, all of this created the Goldilocks conditions for the next threshold, which is the creation of life. And here you have stromatolites. They're still forming off the west coast of Australia, for example. But we have fossil stromatolites from 3.5 billion years ago, and it's a reasonable guess that they existed 300 million years earlier. So, threshold 5 is the creation of life. On at least this planet, probably on billions of other planets and moons in our galaxy and our universe, you get a new type of complexity, life. Now, this is just a hypothesis that arises naturally out of this story. I think many of us have the feeling that this is a pretty fundamental transition from non-life to life. But pinning down what's going on is tough. So let me have a shot at it. This is a type of complexity that can be called active rather than passive. Living things exist in extremely unstable environments. So to maintain their complex structures, they need to be constantly adjusting to those environments, unlike stars, which just basically do their things until everything stops. Same with rocks. So this adds two new crucial elements to the story. First, if they're to adjust to their environments, they need information about the environment. So this is the point at which stuff becomes information. In other words, the structures of the environment become important to someone. So they need senses. They need to be able to detect information. So information enters the story at this point. And the second thing that enters is purpose. This constant adjusting that's characteristic of all living things because of the instability of their environments. Biologists call it homeostasis. But intuitively, I think we have to think of this as purposefulness. It looks purposeful. You have entities now that seem to make choices. So information and meaning enter the story, I think, with life. We have entities not just able to choose alternative paths, they have to choose alternative paths. And the information in genes preserves those mechanisms that help them to make good choices. So information becomes strategic, and purpose and meaning enter the story. And this is a crucial point for the relationship between sciences and humanities, because I think once purpose and meaning enter the story, we're also close to things like ethics. Things matter. It matters to a bacteria, whether it's heading up the gradient of acidity or down it. So things matter. This is also a level of fantastic complexity. Now, I'm not a biochemist, and I wouldn't pretend I understand this, and I advise you not to try to read it. But it's just an attempt to give a sense of the fantastic chemical complexity, even of simple bacteria, like prokaryotes. So this really is a very high level of complexity. And if these arguments are correct, biology and the humanities are dealing with levels of complexity higher than those of physics. And this may be why mathematizing the biological sciences, and even more the humanities, has proved to be so difficult. Maybe it's simply because we're dealing with higher levels of complexity in these disciplines, and we haven't yet found how to use this powerful tool of mathematics that's so powerful in physics, chemistry, other disciplines. Okay, I said I'd follow the energy. Where's the energy that allows such complexity? Living organisms tap energy, most of which comes from sunlight, captured by photosynthesis. And they do this through what biologists call metabolism. Each species has its own particular trick for tapping the energy it needs to maintain itself. So here an egret is chasing a long tom for breakfast. So now, fast forward to humans, and I'm going to skip the whole fantastically rich story of the evolution of life over 4 billion years. Here's life, here are multicelled organisms, and here are humans. How do humans fit into this story? Now, this is the point at which we cross between C.P. Snow's two cultures. I'm a huge fan of Jane Goodall, who has helped us appreciate, as Atsushi's wonderful paper yesterday did, our closeness to chimps, very intelligent, and in primates in general, very intelligent, smart organisms, probably with a rich emotional life, but there's something very different about us. What is it? Well, if we look at energy, here's a difference. Here are the normal biological rules of using energy. A species evolves in a particular, I'm going to say niche because I grew up in England, but when I taught in San Diego and I was talking about niches for quite a time, I realized my students were looking more and more puzzled. Eventually one stuck up their hand and said, "Excuse me, Professor, what's a niche?" I thought, oh my God, I'm in trouble. So I started explaining and she said, "Oh, you mean a niche?" Okay, so when I say niche, I mean niche, okay? But I'll probably say niche. So a species evolves in a particular niche, with a particular metabolism or way of tapping energy from the biosphere. It's got its own technology. Its populations expand and contract to use up the resources of that niche, depending on the energy flows available with the niche. The niche itself, of course, may evolve. Then eventually the species will go extinct, or the niche will vanish, or they will evolve to find new ways of tapping energy. Those are the normal rules. And it generates a familiar pattern, something like this. This is just iconic. A new species appears, its numbers grow exponentially until it's filling the niche. And then they fluctuate around that level, and then eventually somewhere over here it's going to go extinct. That's normal rules in the biological realm. Now here's a graph of human population growth. I could very easily have extended it over 200,000 years, so that'll take it over there. Straight line, okay? Now I hope it's immediately obvious something different is happening here. There's actually growth throughout the Paleolithic, certainly in the last 60 or 70,000 years. We can be pretty sure that the long trend is towards growing populations. Here we're probably talking about 5 million, 10,000 years ago, the last of the Ice Age. And then suddenly, populations take off. And then this happens in my lifetime. We go from under 2 billion to over 7 billion in my lifetime. So this is an exponential curve, and it looks very different from what we see in the animal realm. So what is going on here? What makes humans different? Well, here's a hypothesis, and it's collective learning. It's a sort of way of describing in general terms what must have happened. The details of how it happened we don't yet understand, although once again I thought Atsushi's wonderful paper was pointing in many of the directions we need to go. So here's the hypothesis. Many animals communicate, but they communicate inefficiently. Now what I mean by that is if you think of a game of telephone, you know, someone says something to someone else, they pass it on, they pass it on. An inefficient game of telephone is one in which the information vanishes within, say, 4 exchanges. An efficient one is one in which information can survive lots of exchanges, and it's sort of conserved. Now, what seems to have happened is that in, say, chimp communities, information leaks away as fast as it comes in. So there's no long-term accumulation of information within the community as a whole. Most learning is individual. It's not collective. With humans, we seem to have crossed what may have been a very small but immensely significant threshold. Our communication system became efficient enough, precise enough, it acquired the bandwidth needed so that information could be preserved reliably across many generations. Now this changes everything, because it means that information, if I have a smart idea, it can be preserved in my community even after I've died. Information can accumulate from generation to generation. There's a sort of cultural and technological ratchet that has appeared at this point. Now, this is utterly transformative. Here's just one way of describing why. It accelerates information accumulation by orders of magnitude. And remember, information is what living organisms need to handle their unstable environments and maintain their complexity. In the biological realm, genetic information accumulates over millennia, over millions of years. In the cultural realm, the human realm, it can accumulate within a lifetime, it can accumulate instantaneously on the internet, and it does so at an accelerating rate as humans find more and more ways of accumulating information. Now, this began in the Paleolithic. This is not just a modern process. It's, you know, Moore's law began 200,000 years ago. So let me show you what I mean. More information means more control over more energy and resources. So we now have a species that instead of hitting a ceiling, will keep acquiring more energy. It'll keep expanding into new niches. Now, here's the chimp range. This is normal animal behavior. We have no evidence that they have significantly spread beyond that niche in several million years, okay? That's why we don't do chimp archaeology, incidentally. There's not much archaeology to do. Here's the range of early humans, but then we start watching them in the last 100,000 years moving out of their East African savanna homelands, occupying seashores, tropical forests, desert lands. Then from 60,000 years ago, maybe from 100,000 years, they start spreading. Now, look at this. They crossed this body of water into Australia, probably 60,000 years ago. They enter Ice Age Siberia. Now, I can ask my students, if I dumped you in Ice Age Siberia, how well would you go? You need technology. You need knowledge. So this is a species which collectively is accumulating more and more information. Each community may not be doing that, but collectively they're accumulating more and more as they spread around the world. And of course, collectively, they're controlling more niches, they're controlling more information, they're controlling more resources. That is the form technological change took in the Paleolithic. And it's an incredibly important story. Then 10,000 years ago, collective learning generates a whole new suite of technologies that we call agriculture. These new technologies, within the story as I'm telling it, can be thought of as an energy bonanza. It's a bit like an oil strike or a gold strike. Here's what agriculture does. Fusion reactions in the sun's core generate energy. That energy pours into surrounding space. Photosynthesis captures some of that energy. And what humans do through agriculture is they grab a larger and larger share of the energy flowing through the biosphere. They do this by changing their environments. They remove species they can't use. They increase the production of species they can use. End result, humans get more energy. Now, with more energy, you can get more humans. So populations increase. You get villages, you get towns, you get cities. You end up with a whole kit and caboodle of what historians call civilization. This is the driver of the last 10,000 years of human history. All the things historians normally study. And collective learning itself is driven with more people, more diversity, more technologies, more exchanges. You get innovation. The rate of innovation increases. You get horse riding, you get improved transportation, communications, you get printing. But there's a limit to the energy available under this organic energy regime, as the wonderful English historian E.A. Wrigley calls it. If you, most of the energy comes from wind, water, wood, and human and animal labor. This is all ultimately comes from the sun. If you burn a piece of wood, you're probably extracting energy generated or captured within the last 30 years. Right? If you burn a piece of coal, you are releasing energy that's been accumulating over 300 million years. That's many orders of magnitude different. So discovering how to use fossil fuels, again, is best thought of, I think, as it's like a gold strike. This modern world is the product of a kind of global gold strike. It's an energy strike. The organic growth was limited under the old regime. And we know this because there was enough resources generated by agriculture to support wealthy elites. But I think there's good reason to think that the majority of the populations of most societies did not increase their per capita living standards or consumption of resources throughout most of the agrarian era. Most of the increase was controlled by elites. And then we watch this. This is per capita growth in the last, well, actually, that's just in the last century there. That's the difference, this staggering increase in the amount of energy available. So collective learning has generated a sort of energy bonanza, like a gold strike. With all the dangers and possibilities of a gold strike, humans discovered how to tap this staggering store of energy. E.A. Wrigley writes, an industrial revolution is physically impossible without access to energy on a scale which does not exist and cannot be secured in organic economies. My colleagues, historians, have talked about explaining modernity for 2 centuries and more. Most of the discussion is about economic efficiency, driving innovation. I'm tempted to say it's fossil fuels, stupid. And that's E.A. Wrigley's argument. And Adam Smith and Ricardo both knew this. They did not predict sustained growth. So this energy rush, and again, that graph, again, this is just a way of giving a feeling for the orders of magnitude we're talking about here. And this is what's created the Anthropocene, this modern era in which a single species dominates biospheric processes, geological processes, climatological processes on the surface of this planet. And this graph charts per capita control of energy. And by some estimates, we're controlling per capita 100 times the energy we need to survive. Now, to see how significant that is, in effect, each of us has 100 energy slaves. They feed you, they clothe you. Some of them carried me from Sydney to Singapore the other day. I'm hoping they'll fly me back in a few days' time. This is Buckminster Fuller who used that image. We're the first species in 4 billion years to control per capita significantly more energy than we need for survival. That means what's happening now is significant on scales of 4 billion years. We need to take on board what a strange moment this is. And it also means the real labor force in the world today is not 7 billion, it's 700 billion. And that's the source of the better health, the longer lives, the higher living standards for billions of humans today. Now, how significant are these changes? Well, an alien observer would see a planet that lights up in just 200 years, in an eye blink. These huge new flows of energy generating vast increases in complexity and power. And we've become a planet-changing species in the Anthropocene. And these vast flows of energy create dangers, because managing them, managing their consequences, is not easy. This graphic is from the wonderful work of the Stockholm Resilience Center. And what they've been trying to do is chart boundaries that we must not transgress. And they argue we've already seriously reduced one of them, biodiversity, which reduces the kind of buffering of the system. Biodiversity buffers the resilience of the system. So there are dangers. And more for us means less for other species. I won't depress you with long lists of figures of the rates of extinction. Instead, here's a cartoon I like, which I think captures some of this. It was sent to me by my son. This is Noah talking to the crew. So much for the unicorns, but from now on, all carnivores will be confined to sea deck. So we do need to manage a rate of decline of biodiversity that is getting to be comparable to those of the last 5 major extinction events in the last 500 million years. So this is the Anthropocene. It's an astonishing moment in Earth's history. This picture, I don't know, for some reason, this captures this to me, the sense of other organisms thinking, what are they doing? It's an astonishing moment in the planet's history. It's the first time in 4 billion years that a single species has dominated energy flows. And we could transform the biosphere for better or worse. It's as if other species are waiting to figure out what we'll do next. And what scares me is I don't think we know what we're going to do next, because we don't really understand this vast machine we've created. Now, why should we care about this story? Why does this matter? Well, this is why I care. That's my son Joshua, and that's my grandson Daniel. If we get it wrong, this project of managing these staggeringly dense energy flows, if we don't handle it right, we risk degrading the lives that they and their children live. And that's why we really need to understand our relationship to the biosphere. Now, I'm just about to finish. In the remote future, when we humans are gone, will complexity keep increasing? It surely will, for a time. And when I say a time, I mean billions of years. But we also know something else. The first law of thermodynamics tells us that energy is conserved. That means the amount of energy in the universe seems to be fixed. But the universe is expanding. So this is not deep science. Energy is going to be spread out more and more thinly through the universe. And the kind of gradients of energy we've seen helping construct complexity will simply thin out. Living things will vanish, planets will vanish, stars will vanish, molecules will vanish, eventually even black holes will vanish. I'm talking gazillions of years in the future, by the way. I'm talking, go several kilometers beyond that timeline I've shown you several times. That's what we're talking about. We're not talking about the next 1,000 years. And what will happen is the universe will redescend the mountain of complexity, and it'll return to extreme simplicity. Simplicity probably greater than that at the beginning of this story. Now, what does that mean about us? It means we live in a sort of springtime of the universe's history. I think that's good news, personally. I'm rather glad I live in this period, when there were energy flows that allowed the creation of complex things, so complexity can increase. And I want to end with a question. What's the driver? If I'm right about this story, or even approximately right about the story of increasing complexity, what drives increasing complexity? I suspect this is a kind of question that's just below the surface of many of the discussions at this conference. And all I can do is suggest three possible drivers that seem to me to emerge out of this story. The first is gravity. What gravity does is magnify tiny gradients in the early universe and creates gradients steep enough to allow flows of energy that can create new things, beginning with stars, that process. So that's one possible candidate. And it's explored, by the way, in that book I mentioned by Charles Lineweaver and others. The second is that maybe we should be thinking statistically. Maybe it's just probability in time. There's a sort of random walk, a colossal random walk here. If you have energy gradients, gradients of matter, of density, and you have lots and lots of time, then eventually, just for statistical reasons, Goldilocks conditions will pop up in different corners of the universe and will allow increasing complexity. And then complexity can build on complexity. And there's a third that, not being a physicist, I wouldn't pretend to understand except at a rather superficial level. Is it possible that the second law of thermodynamics, which we think of as the driver of simplicity, is actually the driver of complexity? Now, Ilya Prigozhin, who Balázs mentioned yesterday, I think was hinting at this. And there's a young American scholar called Jeremy England who's recently claimed to be able to sort of explain this mathematically. And I wouldn't pretend to follow the mathematics. But the point, as I understand it, is this. Complex things need flows of energy. So what complex things do is increase flows of free energy. As a result of that, they dissipate free energy. They speed up. They're helping entropy on its way. They're helping the second law. They're speeding up. They're bringing that eventual period of simplicity closer than it would have been otherwise. So we are the unwitting agents of the second law of thermodynamics, if this argument is correct. I thank you for your attention.
Thanks, David. That's absolutely brilliant. So we now open the floor for questions. Please wait for the mic. Yeah.
Can I confess that my hearing is not great? So if you ask a question, please speak clearly and use the microphone. Otherwise, it'll be boring. I'll have to ask you to repeat it.
I'm Roland Fletcher. David, that was a remarkable talk. There is a key part of it I'd like to extend, though, because of your last somewhat worrying comments. You wondered why you needed to say when humans came into the story. Well, it's a simple shorthand for it takes 4.5 billion years for intelligence to develop, roughly, on this planet. I think you should chuck the cetaceans in there somewhere as another form of intelligence. The key thing about our intelligence is that it's operational. It's operational. Right. We can do things with it rather than think about the universe in an interesting and delicate fashion. We can mess around with it. What is worrying about that 4.5 billion years is, as Lineweaver points out, we have had planets around since about 11 billion. So there's a rather nasty long period of time for 4.5 billion years of intelligent evolution before this planet even got going. And you're talking about our big information stocks. On the model that I was talking about yesterday, there are players out there in the universe whose energy game is way beyond ours, which suggests that we're a very, very small player in a very, very big game that has been going on for a very long time. And the Enrico Fermi question, where are they, becomes deadly serious.
Absolutely.
We're certainly not, I think, on any of the models we see from Hollywood likely to have aliens invade us. We would be so trivial a source of energy that they wouldn't even bother.
Yeah. Yeah.
We're not in their game at all.
Yeah.
But if your model is correct and it's consistent in the universe and life is common, and increasingly we're told planets are common, we're looking at a problem of a universe that's full of intelligence,
Yep.
that's chewing up energy at an astronomical rate.
Yep. Yep.
We ought to be able to see that. Archaeologists, I might say, specialize in garbage. The answer to looking at the universe is to look for the garbage, look for the rubbish. Any comments?
I've got a friend who, Joe Vorosh in Melbourne, who's doing exactly that. And in fact, there are some cosmologists, I've forgotten the name of the object they look at, but there's a speculative argument that civilizations, whatever we call them, might have learned to tap the energy of whole galaxies and rearrange whole galaxies, and that it might be that we even know the signs we should look for. And I can't remember the name of this object. I don't know if anyone in the room has come across this. And Joe tells me there is an intriguing object that could reflect this. But yes, Fermi's paradox is fascinating. For what it's worth, I'm slightly skeptical about attempts to mathematize these processes, although I do see the logic of them. And I agree with you completely. The logic of this and the logic of astrobiology, which was science fiction when I started teaching, is now serious science, was not just that they're elsewhere, but bacterial life could well be quite a lot of bacterial life in our solar system, at least in the past, maybe even in the present on Europa or planets like that. Therefore, the fact that we've not seen them, despite, I think, 30 years of SETI looking, might be a bit odd. I've met some people from the Future of Humanities Institute in Oxford. Nick Bostrom runs that place. And someone else from Oxford said, you know, they're all as mad as meat axes, which they are, but they do fascinating speculation. And one of the speculations is estivation, which means that civilizations may reach a point where, rather than conquer the rest of the universe, they put themselves to sleep for billions of years, because they've figured out that the universe will be much more interesting if they hang around for a few billion years. I mean, I don't know about you. I find that kind of crazy, but these are brilliant people, and this hypothesis is argued with great interest. I've actually given talks on this, and one of the payoffs that I enjoyed about this was that the question was, I began with the Drake equation and sort of went through that, and the discovery that there may be 17 billion Earth-like planets in our galaxy alone. You know, it has to raise the odds that you're right on this. So I was raising this question: what you'd need to get. The question was about hominids. Humanoids was the word I used. I think the idea of collective learning may suggest a powerful definition of humanoids. Species that are not only very intelligent, because this is the point of my argument, it's not individual intelligence that makes us powerful, it's our collective intelligence, the fact that we can share our knowledge, that we're networked. Most of the stuff in my head and your head was not put there by me. It was put there by other humans over many generations. That's what makes us different, if I got this right. So if you have a planet where evolution runs for, say, 5 billion, maybe 6, 7, 8 billion years, I think there's good reasons to think that something like a nervous system should develop, something like brains. And if I'm right, and that chimps and Neanderthals above all may have been right on the cusp of this linguistic revolution, although we beat them to it and blocked them off by doing that, then there ought to be, so we can define humanoids as species capable of collective learning. Now, if that's true, we can say something about them. we can say that they will become a planet-changing species within maybe just a few 100,000 years. So there ought to be lots of anthropocenes. So we can say that the trajectory of human history may be a trajectory that's been passed many times in the universe. The species that acquires the capacity for collective learning starts invading more and more niches, eventually starts constructing more niches, becomes more powerful, and eventually dominates its planet. But that still leaves the Fermi paradox hanging. And at the moment, I don't think anyone really has a good answer to it, you know, but it's a fascinating question, so thanks. Yeah.
I'm going to ask you a more down-to-earth question. And we talked about it briefly the other night. In today's world of science, you have academic communities that define their discipline very narrowly, especially in academia, where, you know, if you're not publishing in these 4 journals and you're not doing exactly that kind of research, we don't want you veering off and doing anything interdisciplinary. Yeah. And God forbid you should actually do something applied. How do we, as a community, help the establishment in science understand that if we want to harness the talent within academia to at least help to really solve world problems, we also have to redefine science broadly enough so that scholars are permitted to do the kind of interdisciplinary research that they want to do.
Thank you very much for that question. I mean, I've been stumbling on this for many years, and the ideology of specialization takes many forms. Many of them are very subtle, many are obvious, but people's personal sense of worth is at stake in conversations like this. So I've got into big trouble as a Russian historian lecturing on the Big Bang. You know, people, what the hell are you doing lecturing on the Big Bang? So yeah, I take it very seriously. I think as a historian, I'd like to think this is part of the evolution of modern scientific knowledge. This is the best I can do to explain specialization. In the late 19th century, there's this tsunami of knowledge in different fields. And actually a rational way of coping with that was specialization. It happened across all the disciplines. It happened in history. You know, so historians focus, I did a PhD on a failed reform in Russia between 1801 and 1803. It went nowhere, nothing happened. You know, that was my PhD. But it was that's the reductionist or specialist strategy. It actually worked very well because there was staggeringly rich research in field after field after field. But I think you can make the argument that a century and so later, we've now got to the point where it's not that we should stop that strategy. You know, the detailed research still has a huge way to go. But more and more of the problems lie between disciplines. As C.P. Snow argued, and E.O. Wilson has argued this very eloquently in Consilience. I personally would like to think that big history is a contribution to this, because what it can provide is first a narrative framework for linking all the disciplines. In other words, a framework that doesn't say, okay, here's a bit of chemistry, here's a bit of physics, and so on, a smorgasbord, but actually a story where the students don't even realize they've moved from chemistry to biology. So it may be able to do that at the educational level. At the research level, this is what I'd love to do. I'm not sure I'll succeed, but our Big History Institute, I'd love to see it doing some of the things that you're doing here. In other words, creating institutes whose goal is to try to bridge the gaps, to provide frameworks to allow research across disciplines. I mean, I have a whole series of subjects. Information is one. Now, I hinted at the possibility that information in a universe without living creatures, it may be a kind of metaphysical concept, but suddenly the structures of the universe can be thought of as information once you have a living organism. So information across disciplines. Does information mean the same thing to mathematicians, as to philosophers, as to cosmologists? Energy. complexity. The Santa Fe Institute, of course, has been doing this for a long, long time. So my hope is that you know, more and more groups and institutions will try to provide the structures, but it's fantastically difficult because the reward structures, the punishment structures, the financial structures, we're trying to set up a journal of big history. The debates we've had are really complex. What format do you use? How do you peer review in big history? We don't know, you know. So thanks for raising that. You know, all I can hope is that more and more scientists will understand, as I think many scientists do, and scholars in the humanities, that there is a payoff to looking at problems across disciplines. And it's not, this doesn't conflict with specialization. This is not an attack on specialization. It's simply saying that good science, I think Einstein's a kind of model of this, needs the capacity to generalize at the largest possible scale, but also to focus on the minutiae that are relevant. Yeah, thanks.
Janusz Hołys, Warsaw University of Technology. Would you agree that for more complex systems, these are not the energy flows, but rather the concentration of information per gram or something like this more crucial? Since if one takes atom of titanium and my mass, then energy concentration in uranium, excuse me, would be much larger. And on the other side, for the living systems, even for the whole Gaia, there's a nearly complete energy compensation. So what, as the planet we are taking from the sun, this is less than 1%.
Yeah.
And as a human, what we are taking as an energy from our neighborhood, it is also, it should be complete balance.
Yeah.
So it is rather the entropical flows or entropic or information concentration, not the energy density that should be crucial parameter for complexity.
Has it switched off? Oh, okay. I think I agree with you. I'm you know, some of the ideas I'm arguing are really very tentative. Eric Chasson suggests this metric of energy, this notion that information becomes strategic with living organisms precisely because they live in unstable environments. So complexity cannot exist without some capacity to do homeostasis, to adjust, and the information you need to know how to adjust. So that information becomes strategic at that point. I guess the logic of my argument is to suggest that information is what is necessary for complex entities in unstable environments to suck out the energy they need. But I agree, you may be right. There may be a point at which,
or vice versa. Maybe energy is needed to concentrate the information.
Yeah, but what's the point of I mean, energy is the thing we know you need to maintain complexity. I think I'm tempted to think of information as a kind of tool to preserve that energy. I mean, even if in the future we find that information is allowing us to use energy more and more efficiently, still we're doing the same thing. We're extracting the energy we need to survive in this immensely complex modern environment, but we're using information to do it more and more efficiently. But that's, yeah, you may well be right. And this is one of the reasons I'd love to have that conference on information. Did information exist in the universe before there were living organisms? I don't know. What would it mean to say that? Some people claim it did exist. Is it possible that an information metric is a better metric for measuring levels, the levels of complexity that Balázs was talking about yesterday? I really don't know. So I thank you for your question. You know, I hope this raises as many questions as it shuts off. But it's a wonderful example of just the sort of question that you're talking about that is not going to be visible to someone who just studies modern economics today or just studies biological systems. You have to be willing, as many people in this conference, to think across disciplines. Yeah.
Would you allow me a second question? Since the time scale that you showed at your first slides it indicates that the time clock is going faster and faster when we are coming to the next levels of complexity. Yeah. So your estimation that we need several 100,000 of years for the next level could be not right. Maybe we need only a few hundred of years or a few years to observe the next level of complexity. Something like intelligent nano-robots could self-organize or something like that, and we would have out of control, and it would be the next level.
Well, I mean, Roland explored wonderfully these sort of metrics yesterday. This accelerating. I'm always slightly worried that there could be an optical illusion here, because this is an anthropocentric story. But nevertheless, some of these exponential curves are real. They're objective. I agree with you completely. So Ray Kurzweil is the person who's sort of described this in the most extreme form, talking about a singularity. It's going to happen in about 30 years, I think, when we download our brains into computers. I'm instinctively slightly skeptical of these metrics, but nevertheless, in the teaching of big history, one of the wonderful things that's happened is I've learned from high school students, and one of the things I've learned is this great question, which just seeped up from the schools: what is threshold 9? Now, again, I don't want to fetishize those 8 thresholds. They're convenient. They can generate discussion. A biologist will immediately want to put eukaryotes there, or multicellularity, or the emergence of sexual reproduction. Planetary astronomers will want to add phases and so on. But so I'm shifting ground here a bit, because it's educationally, I think, very powerful to have young people asking this question. We know what the candidates are. I mean, I've just been reading Nick Bostrom's book, Superintelligence, which is very scary and a bit closer to Ray Kurzweil than makes me comfortable, although Ray Kurzweil is an optimist, Bostrom's a pessimist. My own instinct, for what it's worth, is to think of sustainability in optimistic moods. Will we find a way of actually managing energy flows in ways that can give us a good life? This is why I've been trying to persuade Jan to have a conference on the good life. But there's also sustainable in terms of the biosphere. So it's a fantastic question. I wish I get students who email me and say, so what is the next threshold? And I have to be very boring and say, I'm afraid I don't know. You're going to be around, I'll probably be off.
Thank you very much, Raymond Kwok here. David, I met you on the first night, and then subsequently, I took a look at your TED.com, 20 minutes or 18 minutes of history. Fantastic. I have questions, basically. We all talk about the Big Bang, but there's no scientist which is trying to explain anything before that. Everything he says is a black hole. And, are you able to share with us some of your thoughts, what happened before that Big Bang theory, or anybody else in this audience?
Sorry.
Yeah, and then the second one is rolling forward, because you have explained the big history between that and now. Rolling forward, I think just now you mentioned about singularities. Do you think that mechanical developments should be superseded by biological development or chemical? Because I think that, rather than a mechanical world, it will be evolved further down the road. Thanks.
Okay, thank you for your questions. I'm tempted to say, is there a cosmologist in the house? No. Okay, well, I'll have a shot at that first. I think there would be a broad consensus amongst cosmologists that we can tell a rigorous, evidence-based story from about, now let me try to get this right, 1 to the minus, a billionth of 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 a billionth, I've lost count, of a second after the Big Bang. We can tell a rigorous story, and we have evidence. Before that, in other words, at the moment of the Big Bang, we don't know how to deal with it, because that's the point at which you need to combine quantum physics and relativity, and we can't quite do it. The equations go berserk. You get all sorts of infinities in the equations. We don't know how to deal with it. But it's not quite true to say that cosmologists don't think about it. They think there's a huge amount of, I think we have to call it speculative thought. String theory is an example. Supersymmetry theory. Multiverse talks about, this may be a tiny corner of a universe that keeps budding off new universes. At the moment, those theories are kind of mathematically interesting, reasonably consistent, but we don't have direct evidence for them. There's a wonderful theory by a Canadian cosmologist, Lee Smolin, which is about evolutionary cosmology. His argument is that black holes are one, and this is apparently, he's a serious cosmologist, black holes are one side of a new universe. If you see a black hole, then the other side of it is a universe. So this suggests a sort of Darwinian story. Each universe may have slightly different parameters. Gravity may be slightly more powerful or weaker. Electromagnetism may be slightly more powerful or weaker. Martin Rees has written wonderfully on these parameters. So you have a new universe. Now, in the beginning, those parameters may be all over the place. But a hell of a lot of universes will be so simple, they'll vanish within a split second, or they will never generate stars, and therefore they won't generate black holes, so they're sterile. So this is Darwinian. Only those universes that have the range of parameters, which is quite narrow, that will allow them to create large stars, and therefore black holes, will reproduce. So hang around a few gazillion, I don't know what the term is, gazillions, or Google-illions of years since the first universe appeared, and you'll find that a remarkable number of existing universes all exist within a narrow parameter. And those narrow parameters are also the ones that allow complexity and maybe allow life like us. So there's lots of fascinating speculation. Well, the final thing is, watch the Large Hadron Collider. The Large Hadron Collider, just outside Geneva, CERN, has been shut down for, I think, 2 years, and they're powering it up. It found the Higgs boson last time, fundamental piece of nuclear physics. Many physicists are quite optimistic. It will now have, I think, twice the power, that it may be able to detect entirely new particles. With more power, you can detect heavier particles. And it might, yes, some of them are optimistic that this might just give a glimpse beyond that first moment. But as a non-physicist, I can't say any more than that. Yeah. Thanks for the question.
Yeah, actually, I have a piece of good and bad news to share with everybody. The news is like the food, I mean, tea, coffee will not be ready at least until 10:30. So bad news, like there will be no food, tea, or drink at least until 10:30. Good news, like we will have a bit more time to ask a few more questions. I think we would have, but maybe I don't want to exhaust our speakers, so I think we will allow 3 more questions.
I'm happy to go on forever. But let's see.
Yeah. So, yeah, any question?
Thank you for your speech. You gave a marvelous perspective on complexity. So my question to you is, what would you advise to the worldwide research funding organizations and to governments in organizing a research agenda concerning the complexity of our society and environments? I would say that we are in a kind of urgency with that.
Yep.
And what would you advise then when they ask you in Australia and say the research funding?
They don't ask.
What the hell should we do?
Yeah.
You have a view on complexity there. How should we organize the research agenda in Australia and the US, for instance? What would you say then?
I mean, I think a lot of research funding agencies are sort of aware of this, but it's a really hard problem. So I think it's one of those problems they sort of, there's not enough pressure, I think, from the scientific world to do this. Now, climate change debates may, because climate change is a wonderful example of territory where you cannot just do it, specialization by specialization. You need people who think across disciplines. For what it's worth, and I think this is why, apart from, this is why I've actually, the World Economic Forum seems keen on these ideas, because I think they accept, and I think quite a lot of research agencies already sort of accept, that we need to go towards more transdisciplinary research. My advice would be to bring scholars who are anchored in different disciplines. I'm not against disciplines. That anchoring is immensely important, around important themes. I mean, and this conference is a wonderful model of exactly that. I'd say, you know, do it the way they do it, you know, NTU.
Do you think Jan Fassbinder is going to save the world then?
Well, yeah, I mean, look, actually saving the world ought to be the title of every conference at the moment, because if half of the science is right, these are very dangerous times. You know, I don't like to be too gloomy, and I could be very wrong, as Paul Ehrlich turned out to be very, very wrong about population. But and personally, I'd like to think that teaching big history in schools, because the people who are going to probably crack some of these problems are 16 or 17 at the moment. And that's why I'd love to see this agenda taught in schools, because I think students who know this story, have some familiarity with the story, it'll just be so natural to think across disciplines. You know, resistance to transdisciplinarity is nil amongst young students. It's most powerful amongst my own established historian colleagues. Less powerful, I think, in the sciences. Sorry.
So that leads to my question, which is, what are you seeing as the impact of big history on the standard history stories that we've been telling?
On the standard history story, well, okay. Try not to turn into a preacher at this point, but H.G. Wells wrote The Outline of History, which was an attempt at big history in 1919, and he wrote it. His argument was, we now have such terrible weapons of destruction that if historians in countries throughout the world keep teaching students that history is about national identity, they're teaching the subliminal message that we humans are organized in competing tribes, and your loyalty is to your tribe. As long as national histories dominate curricula throughout the world, which they still do a century later. So he wrote this with the idea that to get a sense of a history of humanity, that humanity has a shared history, and I hope I've captured some of that shared history in this, you need to talk about the history of everything. Now, it couldn't be done in his time, but I think the same logic is true even more powerfully. We now have nuclear weapons. We have weapons that could, I remember living through the Cuban Missile Crisis. We came very close. You know, we got through the 20th century. There was a lot of luck involved. We could degrade the biosphere in 24 hours. There's still 1,000 nuclear weapons on hair trigger alert. They could be launched within 15 minutes. So I think we desperately need a history of humanity. What's the impact in actual schools? I hope, I don't think I could document this, that it'll make it easier for students to not only have a national identity, but also to identify as members of a humanity and not think of that as a kind of thin or superficial concept, but to think of humanity as a richer, more rigorous concept than American human or Australian human or Singaporean human. So I'd like to think that it can offer another identity, which is human. And in a globalized world with global problems, we desperately need people to be thinking about how humans can work together. I mean, it may sound naive, but you know, we have to do it. As long as climate change negotiators go into the negotiating room thinking primarily, I'm defending US interests or I'm defending Australian interests, we're not going to get anywhere. If they go in equipped with a larger identity, there's a sporting chance they'll actually spend more time looking for the middle ground. You know, that's more a statement of conviction and hope rather than the response. You know, so.
I have a very last question.
So just a final question. You said the origin of life was about two things, information feedback and purpose. which then led into ethics, etc. Very quick question, what's the purpose of life?
You won't accept 42, will you? No. Completely purposeless. I mean, I'm actually trying to write a paper which was prompted by, I was invited to give a talk on big history at a theological college in Atlanta 2 years ago. I was a bit nervous. I mean, at first I said, I think you've got the wrong person. Don't be fooled by my surname. I think you've got the wrong person. They said, no, we've got the right person. We have an annual lecture on science and religion. And these are Baptist theologians. I had the best time with them because theologians ask questions at these scales. Now, I'm not comfortable with their answers, but they were very, they were well-informed, they were scientifically literate, very keen to find a kind of common ground between a very liberal Baptist theology. Actually, I was denounced by someone at the back, and they said to me, they more or less frog-marched that person out of the room. They said, those people are our nightmare, not you. Yeah, the meaning of life. I mean, the point is, it turns the question around, because what it says is we have now entities for which things matter. In other words, entities that have to make choices. The bacterium that goes the wrong way is a dead bacterium, its genes are lost. So we have entities that care, so that the idea of meaning appears, which is turning the question around, rather than trying to say, what is the meaning? And of course, the purpose is surviving and reproducing. But then there's a whole cluster of other purposes around that, because built into us now is a whole series of mechanisms that make us feel good about some things, bad about other things. So, coping with those mechanisms is a kind of outgrowth of this very simple original mechanism, I think. So yeah, many of my students ask, what's the meaning of life? but that life introduces the idea of meaning is how I'd prefer to put it. Well, yes, but it's almost, you can almost say it tautologically. I mean, in Darwinian terms, it's only things that survive, if you see what I mean. So the Darwinian mechanism generates entities that are designed to survive. But I also, in this argument, and I'm trying to write this up, I think there is a segue to ethical arguments through this. Hume famously said you can't get an ought from an is. And logically and philosophically, he's absolutely right. Biologically, he's dead wrong. We are organisms that cannot just see the world. We see the world with purpose. I mean, I know many scientists would say, no, this is objective. And you can test how true this is by saying, when did you last put in a grant application in which you said, oh, P.S., this research has no purpose, no meaning, no significance at all, dear fund granters. Scientists care. They care about getting it right, for starters. They want to get it right. They care about bad science. So we cannot help caring, given this nature of living organisms. And that itself may be enough of a basis for a sort of naturalistic or humanistic ethics. And that's why I put up this picture of my grandson. I hope it doesn't sound like a crude or cheap trick. I take it very seriously. That's why I care, because I'm a biological entity. And I would not stretch the argument to Daniel's great-great-great-great-great-great-great-grandson. Frankly, I don't care. But 2 generations away, yes, I do care, because of the nature of the organism I am. I don't know if that's a decent answer. But I think there is a segue into serious discussions about ethics and meaning. And many of the students who do this course, they understand this is just seeing the story as saturated with philosophical questions and with ethical questions.
Yeah, I'm afraid we have to stop here. More issues and questions can be discussed during the coffee break. I hope coffee is already here. Please join me to thank our speaker.
Thank you very much.
Yeah. And allow me to present this small token of appreciation.
Thank you very much. Thank you so much.